It is section 5.7, implicit methods and implicit differential equations. For the first order initial value problem given in this equation, the Euler method we learned in an earlier section can be rewritten as this form. The left-hand side is a forward approximation of y prime at xn. Now, right side, the base level is xn. So that from the equation, now this nth level, then left-hand side must be y prime at xn. So that this approximation is along with forward value. So yn plus 1 is approximation at xn plus 1. So this value is a forward value, so that this difference is a forward approximation of y prime at xn. So that's the reason this formula is called forward Euler method. Okay. The backward Euler method for solving the initial value problem is defined as this one. Now, the base level is n plus 1. So if you consider the initial value problem, then the left-hand side must be y prime at xn plus 1. This value is representing that value, that level, and y sub n is a value at backward point xn, so that even though these two are the same, this one, along with that right-hand side, must be a backward approximation of y prime at xn plus 1. So that's the reason we call it the backward Euler method. Okay. The forward Euler method is an express method because we can get yn plus 1 directly by using known values. The backward Euler method is an implicit method, and we need to solve the equation here. Now, yn plus 1 is here, and the right-hand side involves yn plus 1, so that you have to solve the problem, for example, by using fixed point iteration. F satisfies a Lipschitz condition in the variable y with a Lipschitz constant L, then the fixed point iteration converges when h is chosen such that less than 1 over L. You can prove this one quite easily. Okay. Here we have an implementation. Apply the Euler methods to solve the following initial value problem. Now, x is from 0 to 1, and for the problem, and the analytic solution is given here. Now, we are using Python. We import first numpy as np, and from numpy linear algebra, we import norm to measure the error. We define f of xy and exact y, and here this is for the Euler method. Now yn plus 1 is yn plus h times f of x yn. That is exactly the formula, and x is added by h for the next level of computation. Okay. Now for backward Euler, now here first we add the h so that the base level is n plus 1, even though we are using here x, that is now xn plus 1. And yn, that yn and h, in this fixed point iteration here, the second yn is used for the formula, and the first yn is used for the iteration so that yn is used to for the initialization of yn plus 1, and then fixed point iteration is performed. And also we try to count the number of iteration for each the level, and then it is added to it, so that here the total number of iteration, the fixed point iterations, will be returned from this function. Okay, and we defined another algorithm, which is the Kronecker-Nicholson. For that one, here Fn is defined, and here rather than separate fixed point iteration, now fixed point iteration is implemented inside here. And for Fn, now we are working on fixed point iteration, that is xn plus 1. Now there's yn plus 1 after convergence. Now Fn is fx and yn, so it is averaged them. And here again, we count the number of iterations. Okay. Now this is a problem setup, beginning point, terminal point, and initial value, and number of sub-intervals. Then h can be defined in this way. Now we have two tolerance. Tolerance 1 is h over 5 is for first order schemes. That is backward-Euler and forward-Euler. And tolerance 2, that is h squared over 5, is for second order scheme, the Kronecker-Nicholson method. Now first we try to find the ODE for exact solution, and we call forward-Euler and measure the error, maximum error, and backward-Euler and measure the maximum error and try to print out the average fixed point iterations. And for Kronecker-Nicholson, and we measure the maximum error, and again the print out the average fixed point iterations. Okay, that is the output. And for the forward-Euler and error, and here for backward-Euler we have error. For this problem, the error for backward-Euler is slightly smaller, but mostly they are around there. And the number of fixed point iteration in average is 1.225. That means that for backward-Euler, the implicit equation was solved in most cases in one iteration. So many people are afraid of solving implicit equations and fully nonlinear problem, but usually by using a good algorithm you can solve the problem very efficiently. For Kronecker-Nicholson method, now error is way smaller, it's about 50 times smaller. So it is a second order algorithm, and average fixed point iteration is 2.225. That requires a little bit more. However, anyway, mostly it converges in 2 iterations. Okay. Here we define the Kronecker-Nicholson method for the first order initial value problem. Now that is defined in this way: yn plus 1 minus yn over h. The left hand side is the same as for Euler methods. Now right side, in nth level and n plus 1 level, the slope values are averaged, so that the scheme has global Kronecker error in order h squared. you should notice that this right side is now here in mid-level. Xn plus half means that mid of xn and xn plus 1 in mid-level, and this average value is the mid-level value plus order h squared, so that Kronecker-Nicholson is formulated along with the base level on midpoint in x direction. Then this difference is a central scheme, and in fact it's the second order central scheme, so that from here second order error and from here second order error, so that whole thing is a second order approximation of the initial value problem. Okay, now this one can be rewritten in this way. Now that formula is implemented in over the program. Okay, now in the program the Fn is defined to be that one. The Kronecker-Nicholson method is also the trapezoidal method, and once the value over there, that makes the method implicit. Now this term is evaluated by using predicted value. For example, this one is now replaced by that one, while n plus 1 star is predicted by using Euler method. Then here we don't have to solve the problem implicitly, and the resulting algorithm becomes the Hume's method, or we call it second order Lunge-Kutta method, right? Okay. The disadvantage to using implicit method is the cost to solve the implicit equations. However, advantages include that they are usually more numerically stable, and a larger step size h can be used particularly for Kronecker-Nicholson method in x direction as a second order, so that you may try to choose larger h, and so it'll work, and that is stable. And also particularly for the numerical solution of stiff equations is working very nicely. For explicit method, and you have to choose a very small h, and however for Kronecker-Nicholson method you can choose a very large type, the step size h. And stiff equation means that here, once in a special direction, now some like a diffusion is happening, then eventually the equations will become stiff. Now here x is usually the time direction in this formula, and if you combine along with differential operator along with special direction, then after discretization in special direction, the system becomes stiff. Okay. Okay, here now we'll consider implicit differential equations. This is a general form of first order ordinary differential equation, and so it is called the first order implicit ordinary differential equation, IOD1. Under certain assumption on f, the general equation can be written as here. Y prime is f of x, y, and y prime. Y prime is involved in the right side, so that yet this equation is implicit. Okay. Now for the problem, the third order Lunge-Kutta method can be formulated in this way. Now we need 3 evaluations, and 1 for 1 weight, and divide by 6, and here the grid size h. Okay. We have to solve here now for K1. K1 is at the left edge point, f, xn, yn, and K1. Okay. That K1 is evaluation of f. Now, if we look at from this one, then that is K value. Again, now, so that y prime itself is also K value, so that you have to put over there K1. So eventually, you have to solve, you have to find the fixed point of this function. And K2 and midpoint evaluation, and y value is predicted by using the Euler method, and again K2, so that the K2 is the fixed point of this function, and K3 is now formulated in this way, yn, and here so that negative hk1 and plus 2hk2, so that is same as basically, okay, this y value is same as yn plus h, and here 2k2 minus k1, right? So along with that combination, we try to predict y value, and again for k3 we have to solve this equation for the fixed point. Okay, so that is now third of the longitudinal method. Of course, this method can be used for explicit differential equation, but for implicit problem, along with this extra the value argument, it can be defined here. Okay. These values can be estimated by applying an iterative method. For example, the fixed point iteration. And for each estimation of ki can be written in this form. So the derivative value, in a sense, that is the fixed point, and it can be initialized by using the last k value, and each time level you will get k1, k2, k3, and then next time level again k1, k2, k3, so that here for k2, k1 can be used for initialization, and k3 you may use k2 for initial value. For next level k1, here the last k3 can be used for initialization. Now the problem is when n equals 0, now k1 has no earlier k3, so that you have to initialize k1, which is representing y prime at x0. You have to initialize this value nicely. Okay. Here, the iteration may stop with a reasonable stopping tolerance. The tolerance is order of h to the alpha. For this problem, now alpha is 3. Now here we have a self-study problem. For this differential equation, y prime appears here again, and y1 equals 0. The exact solution is logarithm x. Apply the RK3 and the fixed point iteration to solve the problem with here the choice of NT. You may use some portions or ideas in the earlier program, and for example, you may start with this one. Okay, so that same portion we define f of x, y, d here. D is y prime. Now exact value is a logarithm of x, and here this is now fixed point iteration F3. For third one, we try to get the fixed point, so I call it fixed point F3. Okay, here you may add some function, and including alk3 and calling, so that you can finish the program with the tolerance h cubed of 5 and the y prime x0, so that the beginning k1 is initialized by 1. Here, okay, this value is small, and no matter what they are, anyway, this is bounded by 2, so that here, that whole thing is bounded by 1/5, 1/5, so that y prime must be around 1 when x equals 1. This value is 1, so that I initialize it by 1. In this case, the maximum error becomes like that for here h is 0.1 and 0.05 and 0.025. You can finish the implementation. Also, it can be a good project. In fact, a small project. Okay. That's the end of the section. Thank you.